In this video, we're going to be talking about continuity. So if we're given the graph of a differentiable function, y equals f of x, we say that the function is concave upward if the derivative of the function is increasing. So if the derivative of f increases, we say that the function is concave upward. It would be concave downward if the derivative is decreasing. So you can kind of take a look at these curves here. So you see we have what we would, from pre-calculus and other courses before, we would say we know that this is concave upward. But how do we determine this through calculus? Well, that would be from the derivative. So if the derivative increases, then that tells us that our function is concave upward. So you can see we have our slopes here, right here, and here. So it goes from a negative and it's getting increasingly more positive. So maybe like the slope there is -1/2, maybe there it's 1, 2, and such. So you can see like numerically the value is increasing. Versus something like this that's concave downward, here we have something with a positive slope, and then we have a negative slope, and then an even more negative. So maybe it's something like +1/2, -1, -2. So you can see the slopes there are decreasing. So when slopes increase, that tells you have concave upward graph. And then again, remember, it's the derivative is increasing. That tells us that f is concave up. And then when the derivative decreases, then f is concave down. Now, if you're looking at something like this, we can see that we have this function here. It kind of looks like a cubic function. This blue portion of my graph is concave up, because if we were looking at my tangent lines, you would see we'd have something where the tangent lines are increasing, right? Now this is like a steep negative, so it's something like -2 and then -1 and then 0, and then they're getting more positive here. Maybe this is like 1/2. So while it's going from it's like steep and then not as steep and then it's getting steeper again, it's still increasing in value, right? But when it changes, so now then we have this point where it changes, and now it's going to start decreasing in value. And so that point where it changes is called an inflection point. So the inflection point is a place in your graph where your function changes concavity from concave up to concave down, or vice versa. Okay. So really quickly before we move on, what's the difference between f prime being greater than 0 and f prime increasing? Well, if f prime is greater than 0, that means it's positive. And when f prime is greater than 0, that means that the values are positive, right? So the value is positive. And more importantly, it tells us that the function f is increasing. So when the derivative is positive, f is increasing. If f prime is increasing, so if f prime is increasing, just like we know if f is increasing, then its derivative is positive. So if f prime is increasing, that tells me that the second derivative is going to be positive. Now, the second derivative is kind of what indicates concavity, and we'll see this in a little bit. But we're told here, right, if f prime is increasing, if the function's derivative increases, then f is concave up. So if f prime is increasing, this tells me, first of all, my second derivative would be positive, because like we saw here, if the derivative was positive, that means that f was increasing. So if this is increasing, then its derivative is going to be positive. But it also tells me that f is concave up. Okay, so how do we test for concavity? So just like we were looking at in that last little part, it's going to deal with the second derivative. So the test for concavity is basically going to help us determine whether a portion of our graph is concave up or concave down. So in this, we need a function that's twice differentiable. Basically, twice differentiable just means that you can take its derivative twice without having any issues. There's no areas where the derivative is discontinuous or anything like that over the interval that we're trying to differentiate on. So it's twice differentiable. So we would say that the function is concave upward. The function f is concave upward if the derivative is positive for all values in that interval, and it's going to be concave downward if, the second derivative. So if the second derivative is positive, then the original function f is concave upward. If the second derivative is negative, then it is concave down. Now, another way to kind of think about another way to kind of visually see concavity, if we look back at this function here, let me clean this up a little bit, get rid of these. So something that's kind of interesting is if you have a function that's concave upward, your tangent line is always going to lie below your curve. So you can see that in all of these, my tangent line or my curve lies above the tangent line. Whereas when it's concave down, the tangent line is going to be above the curve. So that's an interesting kind of fact about this. It's not the definition of concave upward and downward, but it's something nice that you can see when you're dealing with concavity. So if the function is concave upward, the tangent line lies below it. If the function is concave downward, then the tangent line lies above it. Okay. So let's go ahead and determine the intervals on which the function is concave upward or downward. So to do this, we're going to have to find the second derivative of f. And then we're going to do kind of like we did back in the first derivative test. We're going to use this table of values to help us determine whether the function is concave upward or downward. So this is concavity, the conclusion that we're coming to of our original function f. That's going to be our conclusion. Okay, so what is f prime? So we're going to have to use chain rule in this. But anytime you're taking the derivative of an exponential, it's just the original exponential first. So negative 4e to the negative x squared over 8. And then since the since the power is not just x, we're going to multiply by its derivative. So the derivative of negative x squared over 8, we can just use the power rule, is going to be negative 1/4 x. So this is going to be our first derivative. The negative 1/4 and the negative 4 can kind of cancel each other out. And we're actually going to get that the first derivative is equal to x times e to the negative x squared over 8. So that's the first derivative. Okay. Second derivative, we're going to have to use the product rule. All right, so second derivative. So it's the first function times the derivative of the second. And we know that the derivative, so it's going to be times e to the negative x squared over 8, right? Because we know the derivative of an exponential is just the original exponential, but then times the derivative of the exponent. So it's going to be times, again, the negative 1/4 x plus the second times the derivative of x is going to be 1. Derivative of x is 1 times this. So it's going to be e to the negative x squared over 8 times our 1 there. Okay. These two terms have an e to the negative x squared over 8 in common, so I'm going to factor that out because I have to figure out what makes this 0. And so I think it's going to be easier to factor this portion out. When I factor that out, I'm left with an x and a negative 1/4 x that are multiplying, so I get negative 1/4 x squared. And in this piece, I'm left with a 1. So what makes my second derivative 0? So set each piece equal to 0. And we get that e to the negative x squared over 8. Where is that equal to 0? And where is negative 1/4 x squared minus 1, plus 1 equal to 0? An exponential is never going to be equal to 0 unless it was having some vertical shift, which this doesn't. So that never equals 0. So there's no value of x that we're going to have to worry about there. I can multiply everything by a negative 4 here, and I'm going to get that x squared minus 4 equals 0. I can add 4 to both sides to get that x squared is equal to 4. Taking the square root, I get that x equals plus or minus 2. So those are going to be the places where the second derivative is equal to 0. So let's go ahead and take a look at our intervals. This function is an exponential, so it's defined everywhere. So we can go from negative infinity up to the first value, and then in between our two values, and then from 2 to infinity. Okay, so picking some numbers, and then plugging in, we just care about the sign. We don't actually care about the value. So plugging in negative 3, that's going to make this positive. or actually, sorry, it's going to be the negative 3 becomes positive, and then we get a negative here. But this whole thing is going to end up being positive anyway, because e to some negative number is just 1 over e to that power. So it's still a positive. So let's go ahead and do this in a different color. So we're going to get like a positive here times the negative 3 squared is going to be positive 9, and then times a negative 4. So that's going to be a number that is bigger than 1. So that's going to be negative there. So this is going to be negative. Plugging in 0, that makes this 0. So that means that's positive. Plugging in 0 here makes that 0, and that's also positive. So we get a positive times a positive. So this is positive. And then lastly, plugging in 3, since the original one was squared, it has the same behavior. So this is going to be a negative there, which is going to give us a negative. So if we recall, it said when the second derivative is negative, the function is concave down. When the second derivative is positive, the function is concave up. And when it's negative, it is concave down. So let's go ahead and summarize our conclusion here. So concave down, it's concave down on the interval from negative infinity to 2 and from 2 to infinity. And then it's concave up on the interval between negative 2 and 2. So that is this first example here. Our goal is the same in the second example. We want to determine the intervals where this function is concave up and down. So we need to start by taking the derivative and actually taking the second derivative. So first derivative, we have to use quotient rule here. So it's going to be the denominator times the derivative of the numerator, which is 1, minus the numerator times the derivative of the denominator, all divided by the denominator squared. Okay. If we want to clean this up a little bit, we can. Let's kind of move this over here. So we have a negative 2x squared and then an x squared minus 1. So this is x squared minus 1 minus 2x squared, which is going to give me negative x squared minus 1 over x squared minus 1 quantity squared. Okay, so this is our function. We need to take the second derivative. So second derivative. Again, we're going to have to use quotient rule here. And we're also going to have to use chain rule. So it's the denominator times the derivative of the numerator, which is negative 2x. Sorry, negative 2x times the numerator times the derivative of the denominator. Okay, so chain rule. So it's going to be 2 derivative of the outside, leaving the inside alone, times the derivative of the inside. All divided by the denominator squared. So when you square this, raising a power to a power, you multiply the exponents. So x squared minus 1 to the 4th. Okay. We can kind of clean this up a little bit. Actually, we have a common factor in all of this of 2x times x squared minus 1. So I'm going to factor that out. So I'm going to factor out my 2x times x squared minus 1. So when I factor that out, what am I left with? So in this first one, I'm going to be left with a negative and then another copy of the x squared minus 1. So negative and then x squared minus 1. When I factor out the 2x, so I factored out the 2x and the x squared minus 1, it left me with this. So it's going to be minus 2 times negative x squared minus 1. And then all of this divided by the x squared minus 1 to the 4th. Okay. So what do we end up with? So this is going to give me negative x squared plus 1 plus 2x squared plus 2, which is going to be x squared plus 3. X squared plus 3. So we get that the second derivative is equal to 2x times x squared minus 1 times x squared plus 3, all divided by x squared minus 1 to the fourth. And actually, we can cancel one of these x squared minus 1s, right? Because we have an x squared minus 1 here, and we can cancel it so that it's now to the third. So let's clean that up a little bit more. So we get 2x times x squared plus 3, all divided by x squared minus 1 to the third. Whew. All right, so we have a lot going on there. But we want to know, where is this equal to 0? We also want to know where it is undefined, just because that's going to kind of help us with our intervals. So 2x equals 0. So we're going to set that equal to 0. X squared plus 3, set that equal to 0. And then set the denominator. So we only really need to focus on the inside, because cubing it's only going to, it's not going to ever change what it equals. So x squared minus 1 equals 0. So this tells me that x is equal to 0. This is never equal to 0. It's like a parabola that shifted up 3 units. And then this is equal to 0 at x equals plus or minus 1. Okay. So my intervals are going to go from negative infinity to negative 1, negative 1 to 0, 0 to 1, and then from 1 to infinity. Right? So you could always write these out in order and then basically think about your intervals that way. Okay, so testing values, let's go negative 2, let's go negative 0.5, positive 0.5, positive 2, and we're going to plug into this. We just care about the signs. So negative here, so it's going to be a negative times a positive divided by negative 2 squared is positive 4, a positive. So we get a negative divided by positive, so that's negative. Plugging in negative 1/2 again gives me a negative there times a positive. Negative 1/2 squared is negative 1/4. Minus 1 is a negative number. To the third power stays negative. So this is going to be positive there. Plugging in 1/2, positive 1/2. That's positive. And then we get a negative actually in my denominator, because I get negative. I get 1/4 minus 1, so that's a negative number. Cubed is negative, so that's negative again. And then picking something like positive 2, that's positive, and then positive. So it's a positive divided by positive, which is positive. So this is concave down. It is concave up. It is concave down and concave up. And then you would go ahead and summarize your result.